Hello everyone, this is Farah Tariq. We're going to explain today a concept in computer networks which is performance of congestion control mechanism for standard TCP versions. We're going to start with our table of content. We're going to have a brief introduction about our topic, then we're going to go into details in transmission control protocol, then we're going to talk about congestion control mechanism and its comparative analysis and its algorithms. Then we're going to conclude our words and our references. For a start, we should get to know what is TCP. TCP is a core communication protocol in computer networks. It provides reliable and ordered delivery of data between devices. It's like connection-oriented or error checking and flow control, which ensures efficiency and accurate data transmission. Then we're going to talk about congestion control mechanism, which is used to manage data transmission in networks. And the evolution of the TCP congestion control was different as it has evolved from focusing on flow control to becoming a fundamental element in avoiding network overflow. And it has a lot of key developments that we're going to go into details on it later on. Its comparative analysis evaluates different congestion control algorithms based on key metrics such as throughput, delay, packet losses, rates, fairness, convergence, time, and robustness. We're going to go into details on this stuff or almost this stuff later on in our explanation. So, we have said that TCP is a core communication protocol in computer networks. But how does this work? We should know first that TCP serves as a fundamental communication protocol within the transport layer. It acts as a connection-oriented language. It encompasses a set of rules and procedures designed to regulate communication between links. As our time is evolving, over the past decade, both computer networks and mobile cellular systems have undergone remarkable expansion, which resulted in substantial increase in interconnected computers and other users' devices, which utilize TCP control. And the most commonly shared protocol is TCP. This has increased the rate of congestion control mechanism that at present is challenging to discern. The congestion control mechanism employed various engines on the internet. It has a lot of types. It's facing a lot of challenges nowadays due to its increased rate of usage recently. So we're going to go into details about TCP variants. TCP variants are a lot like TCP Tahoe, TCP Reno, TCP New Reno, and TCP Vegas. First of all, we're going to discuss TCP Tahoe. TCP Tahoe is the first algorithm that incorporates three congestion control mechanisms: slow start, congestion, avoidance, and fast rate transmission. The slow start algorithm The algorithm's strengths include threefold approaches comprising slow start for gradual increased transmission rate and congestion avoidance to regulate data transmission rate effectively and prevent network congestion. Despite its efficiency, its fast rate transmit upon detecting packet loss. TCP Tahoe does exhibit a limitation. A full timeout interval is required for complete packet loss detection, introducing a slight delay in response to network issues. This characteristic, while effective in error recovery, could potentially impact the algorithm responsiveness. In dynamic network connection, it's crucial to consider this feature and weaknesses when evaluating sustainability of TCP TAO for specific network scenarios. But regarding fast transmission, retransmit and fast recovery, TCP TAO responds to packet losses by initiating a rapid retransmission phase upon the acknowledgement of three duplicate packets. This phase includes the immediate retransmission of the missing packet, simultaneous adjustments of the congestion window threshold. Then it has a lot of limitations. Full timeout intervals for complete packet losses. Then we're going to talk about TCP Reno. TCP Reno has an evolution as it was earlier a variant of TCP Tahoe and it was widely used. It was an early variant of the TCP protocol which incorporates the fast recovery algorithm and remains widely used today. It evolves from TCP Tahoe and excels in managing network congestion through four phases: slow start, congestion avoidance, fast retransmit, and fast recovery. Reno strategically uses packet losses to gauge network bandwidth, employing a conservative approach in the slow start phase and dynamically adjusts the congestion window based on network conditions. While it performs well in detecting and responding to congestion, TCP Reno faces challenges in scenarios with multiple packet losses within a detailed window, leading to adaptive adjustments in the congestion window. So they tried to enhance TCP Reno. To enhance it, they made another one which was called TCP New Reno. TCP New Reno, it addresses the issues of timeout resulting from multiple packet losses. It's an enhancement and congestion window handling. TCP New Reno addresses the issue of timeouts resulting from multiple packet losses within a single data window. It introduces a fast recovery mechanism that allows retransmission of a single packet per round trip time. Notably, New Reno improves the fast recovery phase by remaining in recovery until acknowledgement is received from all acknowledged segments, preventing repetitive congestion window reduction. Despite this enhancement, TCP New Reno still requires one RTT to detect each packet loss, presenting a trade-off in its performance. This chart illustrates the congestion of a TCP New Reno. Then we're going to talk about TCP Vegas. TCP Vegas was proposed in 1994 with a new approach to congestion avoidance. It was proposed as an alternative to TCP Reno, offers a fundamentally different approach to congestion avoidance. It achieves higher throughput by detecting congestion before packet losses occur, distinguishing it from other TCP versions. Vegas introduces unique mechanism in its congestion window control, incorporating distinct phases like slow start and congestion avoidance. Unlike Reno, Vegas checks for congestion by comparing transmission rates to predict rates, anticipating and preventing congestion instead of reacting to losses. While effective in homologous network, Vegas faces challenges in heterogeneous environment due to fairness issues when competing with other TCP variants. Second point we're going to talk about is congestion control mechanism. Congestion control mechanism, in it we're going to discuss various points. But first we should know what is congestion control mechanism. Congestion control mechanism is a critical aspect of managing data transmission in network environment. It's crucial for managing data transmission in network environments. Various methods such as additive, increase, multiplicative, decrease, which is AIMD, aim to increase transmission rates gradually until congestion is detected, followed by rapid decrease. However, AIMD may not be optimal for high-speed networks. The development of congestion control algorithm occur independently, lacking of comprehensive examination of interaction. Basically, congestion, it's like when data congest in the network. The first point we're going to talk about here is TCP congestion control. TCP congestion control is a fundamental part of the TCP protocol, which we talked about earlier. It evolved over time with diverse algorithms, initially addressing flow control TCP, now combine TCP variants and AQM to manage congestion. AQM is active queue management. It drops packets when the buffer is full of signals saturation. TCP congestion control effectiveness rely on this combination. So, its main objective is to avoid network overflow by assessing and determining available capacity. So its main components is TCP variants, responses, active queue management, which is AQM, which we just talked about. So it's very important to manage congestion. The second or third point we're going to talk about here is specific mechanism. Specific mechanism, we have a lot of specific mechanism in congestion control, such as slow start, congestion avoidance, TCP Reno slow start, and congestion avoidance, fast retransmit, and fast recovery. First of all, we're going to talk about slow start. Slow start initiates with a gradual transmission rate increase, exponentially growing the congestion window until reaching the threshold constant SS TRESH. It concludes when the window exceeds or congestion is detected. So a gradual rate increase until reaching the SSTHRESH. Congestion avoidance is the increment in the congestion window linearly until congestion is identified. Is the linear growth per RTT until congestion, limited by increased post-congestion. It concludes its further increase is limited. If congestion is due to timeout, it reverses to slow start until halfway to its state at congestion. Nonetheless, we're going to talk about fast retransmit and fast recovery. Fast retransmit is efficiently handles out of order segments, transmitting when duplicates ACKs indicating packet losses are received without waiting for the retransmission limit. So it handles out of order segments. With the help of it, we have the fast recovery. Fast recovery ensures continuous data flow after fast retransmit, transitioning from retransmission oriented to congestion avoidance, maintaining consistent data flow and preventing abrupt throughput reductions. So it handles out order of segments and help in having a smooth flow continuation to avoid congestion. Moving on to the third point we're going to talk about here is congestion in network environment. Congestion in network environment introduces elements into the network to optimize buffer space in routers. Routers address congestion when the retransmission time expires, modifying the congestion window using slow start and congestion avoidance algorithms. So its main components is routers and TCP layers adjustment using slow start and congestion avoidance. Moving on to TCP congestion control CC algorithms. TCP/CC algorithm aim to optimize various matrices. They are categorized into loss-based, delay-based, and hybrid algorithms, making trade-offs between throughput, delay packet losses rates, fairness, convergence of time, and robustness based on the working environment. So it's designed based on trade-offs and specific to working environment. It's evaluated based on the throughput, the delay, the packet losses rate, the fairness, the convergence of time and robustness. Moving on, we're going to talk about comparative analysis and congestion control algorithms. These synchronized algorithms, like the algorithm we just talked about minutes ago, like Tahoe and Reno and New Tahoe and Vegas and other ones like SAC and FAC. Considering their impact on adjusting the transmission window to prevent buffer overflow, it outlines the evolution of congestion control algorithm, highlighting issues and improvements introduced by various versions. So it faced a lot of challenges like adjusting transmission window to prevent buffer overflow. It has three categories. These three categories are loss-based, delay-based, and hybrid algorithms. Moving on to evolution of congestion control algorithm. But before mentioning it, we're going to give a brief talk about loss-based and delay-based and hybrid algorithms. So loss-based algorithm is originating with TCP Reno. Loss-based algorithm evolved to address challenges in fully utilizing available bandwidth. New algorithms like New Reno, High-Speed TCP, Hamilton, Scalable, Westwood, and others emerged to probe network resources more aggressively while distinguishing between different causes of packet loss. So basically this was a brief intro about loss-based algorithm. Moving on to evolution of congestion control algorithm. TCP Tahoe, the initial algorithm, implemented a fast retransmit phase. Reno TCP incorporates fast recovery procedure. TCP New Reno improved the fast recovery by staying in the recovery phase until acknowledgement is received for all outstanding data, preventing multiple congestion window reduction. So here we use the selective acknowledgement SACs that I just talked about minutes ago. Basically, TCP SACs overcome limitation of cumulative ACKs by allowing the transmission of more than one segment per RTT. The receiver informs the sender successfully received segments, enabling targeted retransmission, enhancing efficiency. Moving on to delay-based that we said we were going to mention later on. Delay-based TCP congestion control algorithm. TCP Vegas, a delay-based modification of TC Reno, predicted network congestion before segment losses. It employs fine-grained RTT estimation, enhancing transmission efficiency. Modifications like TCP Vegas Plus and TCP Vegas -A addresses fairness issues and performance in different network scenarios. So, the challenges they faced here was the accuracy of RTT estimates affected by network factors. And they used the proactive approach here was identifying congestion onset before loss through RTT variations. Moving on to TCP dual and recent developments. TCP dual, it's a delay-based approach that we're just talking about. It's identifying congestion through queuing delay. TCP Dual introduced the use of queuing delay as a congestion indicator. Vegas focused on estimating and maintaining the number of packets in queues. Modifications like Vegas A, Vegas Plus, Fast, VFast, and New Vegas addresses issues and refine features. Recent developments include LOLA and Timely. Here, next, we're going to talk about hybrid TCP congestion control. Hybrid algorithm, fast loss based on delay-based approaches that we just mentioned. Compound TCP combines aggressive loss-based behavior during slow start with a delay-based component during congestion avoidance. YEAH TCP operates in fast and slow modes, leveraging RTT measurements for efficiency. TCP BBR by Google constructs an explicit CC model based on RTT and network delivery rate measurements. So its representatives here were the compound TCP, yeah, TCP, and it used the fusion and loss-based and delay-based strategies here. The compound TCP here, it's an default in Microsoft Windows. It's tailored for high-speed and long-distance networks. It has various phases like aggressive slow start, combination of loss-based and delay-based, and congestion avoidance. And we just mentioned the three of these points in the slides minutes ago. We benefit from this a lot in enhanced network utilization, fairness, and reducing send and delays on packet loss, which help so much in decreasing the packet losses and which happened while networking. Last, we're going to talk about TCP/BBR. TCP/BBR was developed by Google. It addresses throughput and buffers bloat challenges. It has a model explicit CC model based on our recent RTT and network delivery rate measurements. It benefits improved throughput, reduced latency, higher connection quality.